Okay, so what we're looking at now are solar and lunar eclipses. So you spent a little bit of time already looking at the moon phases and how the moon phases work. And if you'll recall, if this is our model of the Earth, and we use a tennis ball for our model of the moon, this is actually pretty close to the right sizes. It takes approximately 4 moons to fit across the diameter of the Earth. So this is pretty close to accurate in ratio-like size. But as far as distance goes, if this were the actual sizes, the distances between the moon and the Earth should be quite a bit larger than this. Although I'm going to keep them about this far apart for the purposes of this demonstration. So just as an example, at this distance, this globe should be like on the counter on one side of the room, and the moon should be on the other counter on the other side of the room. That's about how far apart they really should be. So we're going to pretend they're this close. Now, tennis ball is the moon, globe is the Earth. The heat lamp here represents our sun. And so we know that the moon goes around the Earth in a very predictable pattern, round and round and round. And it goes around roughly every 28 to 29 days. Okay? And as the moon is coming around, we said, and some of you have even asked, why is it during every single new moon, why don't we always get a solar eclipse during every single new moon? And why don't we always get an eclipse during every single full moon? Why doesn't the shadow of the Earth block it or something like that every single time? And that's because the moon, as it goes around at an angle, kind of like this. It's a 5-degree angle, and this is a lot more exaggerated. What I'm doing right here is more than 5 degrees. And it actually wobbles a little bit, similar to the way a coin does when you spin a coin on a table just before it stops. The way the coin wobbles like this, the orbit of the moon is doing the same thing around the Earth a little bit, so that most of the time the moon is either above or below the Earth's shadow during the full moon phase. And the same thing during the new moon phase, it's either below or above the Earth. And so that's why we don't always get an eclipse every time. And so I'm going to turn this way so you can see on the camera a little bit better. Okay. So as the moon is coming around and we're entering into the new moon phase, if the moon happens to be in the same equatorial plane as the Earth as it's coming around and revolving, the moon will pass between the sun and the Earth. And hopefully you're able to see that shadow that's being created right here. The moon is casting a shadow onto the Earth. And you'll notice that that shadow is not covering the entire surface of the Earth. It's covering a portion of the surface of the Earth. And so only a chunk of the Earth can actually see a solar eclipse. Not the entire Earth gets to see the solar eclipse. So you have to be in the right place at the right time. And this happens again during the new moon phases. If it happens to be in the right spot during a full moon phase, as it comes around, you can see that the moon is lit up, but then it enters into the Earth's shadow. And you can see the shadow of the Earth move across the surface of the moon. And as that happens, we end up getting what's called a lunar eclipse. One of the big differences between the solar and lunar eclipse is if you happen to be on the nighttime side of the Earth at that time, everyone on the nighttime half of the Earth gets to see a lunar eclipse. Okay, so lunar eclipse, lots of people get to see. Solar eclipse, only a few people get to see it if you happen to be in the right place at the right time. Okay, now let's draw a couple of diagrams, and I will turn the lights on. Bam, magic, lights on. Okay. Let's title this Lunar and Solar Eclipses. Okay. Now, the word eclipse, we're not going to get super technical here, but the word eclipse is basically meaning that it's being cast into shadow. So it's being blocked. Something is being blocked from view by shadow. Okay, again, not a super technical definition, but that's the gist. Okay, we have 2 kinds of eclipses, and I'm going to draw one, and then I'll erase it and I'll draw the other because I'm going to draw the diagrams kind of big here. You, of course, draw one, keep it, and then draw the next one. We'll start with a solar eclipse. The name has built into it what is actually being blocked. Solar is sun. The sun is what's being blocked. So keep that in mind when you're looking at like an example problem or diagram. the thing that's being blocked is in the name. So let's draw over here our sun, big orb, and then we'll draw the Earth. And obviously my distances and my scales are way off. The Earth should be way further away and the sun should be quite a bit larger. If the sun is being blocked, where should the moon be? Remember, eclipses only happen during a new moon phase or a full moon phase. So it's either here or here, okay? Sun's being blocked, and the moon has to be between the Earth and the sun. Okay? So the sun's light is shining this direction, and as it shines this direction onto the Earth, the moon's shadow gets cast onto the Earth. And this is, in my diagram, if you're standing in this region, this is where you're going to get to see the full effect of the eclipse. Now, what I've actually drawn here, this is actually quite a bit larger of a region than what's actually seen the eclipse, because with the real moon or real Earth and the distances involved, it's more like a region about the size of this dot, and maybe even a little smaller, actually gets to see the full eclipse. But just based on how I've drawn this diagram, we'll pretend that this much of the Earth gets to see the solar eclipse. Now the light from the sun, you'll notice the sun is quite a bit bigger, so sunlight is actually coming not only straight on, like this, okay? Light is also coming in at angles, like this, from these parts of the sun. And when that happens, it ends up creating kind of a different shadow that's cast onto the Earth, and you get a really dark shadow and a really light shadow. And so if you're in this region of the Earth, you get the really dark shadow. You get to see the entire or full total eclipse. If you happen to be here or here, you're getting to see a partial eclipse of the sun. And the different types of shadow have two different names. The inner shadow is called the umbra. This is actually the root for the word umbrella. And umbra is shadow. And so an umbrella was actually invented to cast a shadow, not necessarily to block rain. It was just a happy coincidence that we can use them for that also. The outer or lighter shadow, or the partial eclipse, is called the penumbra, or almost shadow. So we got two different types of shadow. Now, if you need to, go and pause and sketch this down. And if you're good to go, I'm going to go ahead and erase part of this. And then we'll do the lunar eclipse. Again, built into the name is what's getting blocked. The moon, lunar, the moon's light is what's getting blocked. And so that happens during the full moon phase, when the moon happens to be on this side of the Earth. So we'll draw the moon right about here. And the Earth does the same kind of thing, where you have two parts of the shadow, where there's a darker part of the shadow, which obviously is quite a bit bigger than the moon itself. So this is the umbra. So if the moon happens to be passing through the large, darkest part of the shadow of the Earth, you get a total lunar eclipse. But the bottom part of the light from the sun and the top part cast a partial shadow into space, kind of like that. And so while the moon is traveling around the Earth, when it passes through the partial shadow, the penumbra, you'll see a partial lunar eclipse. Now, I'm going to turn the lights off, and you can kind of see how the umbra and the penumbra work. Okay? Turn the sun back on. Okay, so right here, during a solar eclipse, and you can actually see it on the wall right here. You see on the wall, you've actually got almost three different types of shadow. You have a really faint, almost outer rim, and then a sort of faint shadow here, and then a darker inner shadow. The same thing happens with the sun and the real Earth. So this would be an example of like the penumbra being cast out into space, and the darker inner part is the umbra. And as the moon moves into the penumbra, you can actually see a partial shadow cast onto the moon. And then you can see the darker shadow cast on the moon. You can see back there on the board how the moon isn't totally into the shadow of the Earth, so you can see the two different shades of shadow right there. So you got penumbra and umbra. Same thing happens with the solar eclipse. As the moon comes around, you can see, hopefully, a darker inner shadow and a lighter outer shadow. And you can see a total eclipse or a partial eclipse depending on where you're standing. All right.